Today we will talk about diffusion models for image generation. This is a continuation from a previous lecture. So last lecture we talked about the diffusion model, and basically we talk about DDPM, DDIM. We can pick any of that. Now we want to go to say how that can be used for image generation. Essentially, there are two things. One thing is the architecture. We haven't talked about this noise prediction network, what it should be look like. Today we'll talk about that. So the design choice, and then we talk about for image generation, usually you need high resolution. The practical choice is actually working with a lower resolution and using VAE, and then you try to get back your high resolution. So this one saves the computation because diffusion model requires a lot of inference, so that's why. So anyway, so we will talk about these two issues, more on the practical side, and then we will talk about stable diffusion, which is the popular open source package for diffusion model, and that is many people use, including research community, including all the artists and so on. So they want to use that to work on this, work with image generation in the open source domain. The closed source, they have much better models now, both OpenAI and Google. But open source, if you really want to control the model itself, stable diffusion is probably still the model which is the most popular. Anyway, so that's the topics. Yeah, so I will talk a little bit about the quick background, quick recall of the diffusion model, as well as how you want to use that for image generation. Then I will talk about the architecture, which is a UNet that can be used to do this noise prediction network for images. Then this is latent diffusion, which basically try to reduce the computational cost. This is now a standard way to work with image in terms of balancing computation as well as the quality. And particularly, stable diffusion is one which uses this latent diffusion model with things like text conditioning and cross-annotation. So we will talk a little bit about the UNet within the stable diffusion. So you see at least one of these practical implementations of UNet in this thing. And then we'll talk about a little bit other on the practical aspects of that, as well as fine-tuning methods. And then then basically have homework which work with stable diffusion, which you can actually play around with on a fine-tuning experiment. Anyway, so that's about this. So we first should recall this diffusion model, which in both DDPM and DDIM. The idea is that the model repeatedly predicts noise. So in both cases, if you have an image, you will think about this, both noise and the inputs are image-alike. And this is what we want to discuss. So also, we want to say a little bit about conditional generation, right? So in the class we talked about yesterday, the last lecture. So we mostly talk about the unconditioned. Unconditioned is you have this noise prediction. You predict noise using the current noisy image YT and T, right? So you only depend on these two. In the actual applications, like a stable diffusion, you have to have text prompts. You generate the image based on text prompts. So you have a conditioning, right? So we want to also add condition into this, and this one is something we want to also talk about how that incorporated, right? But for this unconditional, you just have a noisy image and the noise level T, right? And then you predict the noise. So this is again, this noise is actually the noise from Y0 to YT, not from YT minus 1 to YT. So this one is something I emphasized last lecture, just say this is because more stable. Turns out that the formula works well. So even though you are predicting the noise for Y0 going to the furthest, to the original image, you can use that to compute, because of this Gaussian relation, you can use that to compute Y minus 1. So for the conditional generation, you're adding a condition, C. C is in the typical image generation, it's a text conditioning. So basically, it's a text, but you can use other conditioning, right? So in a lot of research applications, they so-called class label conditioning. For example, a lot of research on stable or on diffusion models are working on ImageNet. ImageNet has this 1,000 class, if you remember. They have another version has more classes, but let's look at this 1,000 class version, right? 1,000 class ImageNet. Then you say, okay, I will say generate a black cat or whatever, right? So assuming that's a class label, or whatever the class label it is, and then you condition the class label and then generate the image. So this class label condition is used mostly in research, less so in the actual practice. Text prompt condition is certainly used in the actual practice, stable diffusion, or if you look at the OpenAI image generation or Google's Nano Banana, they both they all have this. You can use text prompts to modify your image. Sometimes you also have image itself can be the conditioning, because you say, I want to modify this image, right? I will say, I will add a person to this particular image, or I say, I want to have a higher resolution of a certain image. In that case, you could have an image conditioning. So you can, whatever the image conditioning you come out with is possible. So essentially, the conditioning can be dependent on different things, including image. So this is something which we could use. So anyway, so we in the case we do focus on later on, we will focus on the text prompt condition, particularly in the stable diffusion. We will see how that's implemented. Okay, so that's thing. Before we talk about the actual stable diffusion, we want to first look at the general structure of the map from a noisy image to noise. Noise itself has an image structure, and the YT is an image. If you think about it in the original image diffusion, YT is an image. The noise itself is also image. So you are really thinking about something mapping from image input to image output. This is something which requires special networks. The special networks, you can look at that both in the pixel space now, or we can also later apply this for the latent space. Yes, so-called UNet. Next lecture, we will also talk about another special networks, DIT, diffusion transformer, right? So that is more modern and then nowadays more popular. But for the earlier stable diffusion, the people actually used, like a diffusion 1.5, which we will use in our homework and the later lecture, it is UNet. So UNet you start with the image, YT, right? You think about H, W. H is height, W is width, and C is the channels. I mean, in the typical image, the 3 channels, right? And then you have UNet, and then you go through the HWC as output, the same shape. You can put conditioning. One condition is certainly time step conditioning, which is always there. You need that to be, and also the conditioning C, which is a text prompt conditioning, or some other like a class label, whatever, right? These 2 conditioning may not be implemented the same way, as we will see. So, and this, this basically, is what we want to say. What is the structure for this particular network? And in particular, what is a UNet and why it's suitable for this purpose? If you think about this picture, essentially you take noisy, right, with conditioning and output the same shape, preserve both global and local details, which is for the image. You have a large correlation and the local correlation, right? If you recall, in the image classification, we use CNN, right? So convolution neural networks. And the UNet, they have some geometric structure. UNet is similar to CNN. It's a like CNN-like in the sense of you also have convolution, and basically this is something what we can actually basically this is something we try to base on. And compared to the diffusion transformer, which we'll talk next lecture, of course, that is based on transformer. It's more like a VIT. This is a UNet. It's more like a CNN. So this is a comparison. But we will base on the CNN to get both global and local structures from image. Yeah. So this one is answer called UNet. So here is the original UNet, which in the pixel space, which I can say for now without conditioning, we just see what it looks like and what's special about this, right? So essentially, what is special about this is you have a downsampling and upsampling stage. Downsampling, you can think about it's an encoder. It's like what we have actually done with the CNN encoder before, right? And essentially, you are going shrink and up to some bottleneck, which is smaller dimensional. Each time, when you have a CNN, you have a downsampling also. Downsampling is through max pooling, for example, right? And then you basically, each time you reduce the resolution by 2 until up to some levels. And then you have a smaller network. You can usually, you downsample, you increase the channel, right? So that's a typical design, if you recall what we have done with CNN encoder. Then you have a decoder. Decoder is upsample. Upsample is transpose the CNN, right? Or it's a deconvolution. So each time you go through larger upsample and upsample, and so on. Compare with what we have talked about encoder-decoder structure. This one is not exactly the same because they have a skip connections. So what happens with the skip connection is they actually have a cross, instead of they just going through the bottleneck encoder-decoder, they also add which in each encoder stage, they skip connect to your, for the reconstruction purpose to actually adding this as a signal. And then you combine it with your convolution. So basically, you do add the, when you do the downsampling, you are adding skip connections when you do the decoding. So it's different from a CNN encoder-decoder structure. And the key difference is this skip connection. So this is a UNet. Yeah, UNet try to use skip connection to better preserve the constructions, which basically you say, okay, here is some details you already have. Here is through the bottleneck, and you can actually focus more on the residual effect rather than itself. So this is a connection. Yeah, so basically encoder builds coarser features, and you usually increase the channel and reduce your spatial direction, spatial resolution. Bottleneck, you're starting with the compressed with global information because it's a smaller image, so it's a global information. And then the decoder reconstruct with full information just by doing. But this guy can help you to reserve to make the work of bottleneck easier to construct whatever residual. This one, of course, you can modify it. Instead of a residual, you have a whatever other projection, residual with a projection, and so on. So basically, yeah, this is the key idea of UNet. And we will use this structure, and we will see how it's implemented later on with both text conditioning and time conditioning, right? So later on. But basically, the key difference, again, is they have this connection at a different layer from the encoder you map to the decoder. Yeah, yeah. Basically, this is just a quick mentioning about why you need that. And this one, again, is a main difference from one we talked about early in the lecture, CN encoder and CN decoder, right? CN encoder, CN decoder. We have that when we talk about the VAE and so on. But here it's resolution is from. Essentially, yeah, basically you're making your job when you do the decoder easier by using staged information from your encoder. So that's essentially this, yeah. Okay, so basically, yeah, span stale and so on. I mean, therefore, this one, you adapt that from the image to image to noise. Noise, you can think about it as an image. So you adapt that to this, and this make it easy. So, okay, so this is roughly what it is, and the key is you have this connection at the same level from encoder to decoder. So let's talk about the latent diffusion. This actually, again, is a simple idea, and they have. I think this paper has two things in that. One is this simple idea about using latent when you do diffusion in the latent space. Which saves. Another thing, they have some modification of this UNet, which is consistent with stable diffusion implementation, because stable diffusion actually is the first version is with this paper. Yeah, it's just a more large-scale version of this paper, and then they gradually evolve from there. But this is a well-known paper, and the idea latent space is also used for other things as well. So first, compressed image with a pre-trained VAE. This VAE is slightly different than the VAE we talked about. In the VAE we talked about, we compress an image to a vector, right? This is a compressed image to a smaller image. So this is basically what it is. For example, the typical version talked about in this paper is you have input image of 256 by 256 by 3, right? 3 is RGB. Then when you compress that, it becomes 32. So it's a downsample by a factor of 8. 32 by 32 by 4. So you increase your channel a little bit from 3 to 4. But you are spatial-wise, you are downsampling from 256 to 32. So basically, then you can work with this smaller space. So the idea is, but a smaller space still has an image structure. It's a smaller image of 32 by 32 by 4. This is called latent image, right? Because you probably cannot really see exactly what that image visually, but it's in the latent space. You can compress that VAE, and this can be pre-trained. So this one you pre-train, and then once you do that, you run diffusion in this latent space. It's still a image, smaller image, 32 by 32 by 4, Therefore, you still need a UNet because they still have a structure. So this is an idea. VAE also regularizes the latents towards approximate Gaussian distribution. That's why you use VAE instead of autoencoder. The reason, if you recall, VAE started with a probability model so that in the latent space, the image looks like a Gaussian. It's similar to a Gaussian. And in stable diffusion, of course, we want to diffuse to a, I mean, it's an approximate Gaussian. It's not truly a Gaussian because, VAE doesn't have enough power to make it exactly like a Gaussian. But it's approximate great because it's similar to the Gaussian, so it makes the diffusion easier because the diffusion want to generate from Gaussian to your targeted distribution, right? This targeted distribution, if they say, oh, it's not too far away from Gaussian, then making this diffusion in the latent space easier. This is why it's used VAE, which basically the whole purpose about this VAE, the variational part is it's so that the latent distribution is similar to a Gaussian. Here is the pipeline. So the pipeline is the following. So you first you have an encoder. So this is your pixel space image X, right? Goes to this encoder, and then you go to latent space. And there are some conditioning. Conditioning we'll talk about that later. Then gradually after you are doing diffusion, you have a decoder back to this image. Both encoder and decoder are just on the image only. They do not have a conditioning in there. So basically, VAE, this VAE is on the image only. So they hope to reconstruct image good enough so that this they have a small reconstruction error, but they are not conditioned on text. Okay. Conditioning is actually in the middle. So this is where. So latent diffuse space, right? You start with a Z. This is your original latent image now. You do a diffusion process, adding noise, which is, say, DDPM, DDIM, right? And then you add that to your noise ZT, which is in the latent space. And then in the generation step, you start with a Gaussian. This one hopefully is like a standard Gaussian. You can add conditioning now, and then you are working with a UNet-like structure. But this one is a hybrid UNet. It borrows some ideas from transformer. Basically, if you look at the QKV, this is a concept of a transformer. So it does have a hybrid UNet with ideas coming from transformer, coming with attention, so that each step is a noisy network, right? This one is, say, at any time step, you go through this network, which we'll talk about next. And then you generate noise prediction. And then you use DDPM or DDIM generation algorithm with this the noisy to generate the denoised image from YT Z, in this ZT to ZT-1 and ZT-2 and so on. Gradually you get a Z, which then you use the decoder. So basically this is roughly the pipeline. It's pretty straightforward. If you think about that, it's just in one sentence, you say, first use VAE to make your high resolution image a low resolution image. And then you do diffusion in the low resolution image. And then you map back to the high resolution. So this is essentially idea. And certainly with a low resolution image, you have a better training. You have a better generation. Generation is faster, right? So basically, this is how it works. And then this is the first idea. And basically, the paper says, oh, this works very well. So you can use practically generate a pretty good high resolution image using this lower resolution image. So they showed some examples how well it does. But also, besides this shows how well it does, it also says this modified denoising UNet, which to do with text prompts. How do you use that to condition on text prompts? So this is another contribution of this paper. They have a specific structure. And this one is a hybrid of UNet and with ideas coming from transformer. And clearly, I mean, as I mentioned, later on in the next lecture, we'll talk about the DIT diffusion transformer, the purely transformer. This one is a hybrid of a UNet and with element of transformer. It's actually mostly depend on UNet, but some part of that coming with transformer. Okay, so this is the idea. Yeah, basically, as I mentioned, the original one and also the one in the stable diffusion, if you start with 256, it's a downsample by 8 to be 32 by 32 by 4. If you have a 512, it's a downsample by 8 will be 64 by 64 by 4. So roughly, it's a downsampling by 8. It's something which without hurting your quality. So that's that's basically idea. Yeah. And if you do even higher resolution like 1024, then you probably have a higher the latent image. So essentially, you cannot downsample indefinitely. You just downsample by certain ways so that it's a reasonable. So run diffusion in the latent space, not directly in the pixel space. So this is this is essentially how it works. Okay, so we will talk a little bit about more details about that. Then we will move to stable diffusion once we talk about that. Actually, yeah. So stable diffusion is just the implementation of that. So we just doing the mainly. This one has Hugging Face again. The diffusers package Hugging Face of transformer and also diffusers, and diffuser is one which you can easily apply for the stable diffusion pipelines. The main components of that text encoder, the clip-based, latent space diffusion UNet, which we mentioned, right? So which there's a VAE autoencoder, autodecoder, right? So I mean, if you are interested in text generation or image generation, right? You can always use this VAE encoder decoder. So people heavily use that. So instead of you work with a high resolution image, you can use that to work with a low resolution image. So a lot of actually the research work use these, not necessarily their UNet or whatever, but for example, the IP paper, right? They switch that to the diffusion transformer, but they work with the same VAE. So because this already pre-trained, you can use that. Sampler, they have this is for generation. There are training routines and generations, and basically they have some scheduling and so on. So there's they have modularized the scheduler or whatever. So but anyway, so this is what this package you can get, and you can use the individual components, right? For example, you can use this text encoder and or something. For the UNet. This description it's similar. I mean, basically it's the same as this latent diffusion paper, but because they already have the Python code, so you can take a look at that code. Just say, okay, how it's actually implemented. It's roughly the same as what's in the paper, but basically, paper is there is a noisy latent image, right? So think about in our earlier picture, it's a 32 by 32 by 4, right? So encoder decoder, rest block plus upsampling plus skip connections, right? Skip connection coming from this idea about UNet. This is encoder. This is a decoder. This is slightly different than the standard CNN, right? You're adding a ResNet. You're adding a little bit transformer. We mentioned you see that the QKV, which basically coming from the transformer, especially it's used to be cross attention to the text prompts, right? So, yeah, so these are two components are a little bit different than the standard UNet we mentioned earlier. We will say a little bit, and the rest components, it's just a variation of your CNN in some ways. So we'll talk a little bit about that. Basically, we just, I mean, this one just for your information only. The details, if you're interested, you can really just look at the code or whatever other things. But basically, I will just quickly talk about that so that we have an idea about how it's implemented. So So text is a clip tokens, right? And then you have a cross attention. And basically, this spatial transformer is just of certain blocks. This includes not all the blocks. So this is a design choice. Time embedding is injected to every res block. So basically, this is text through cross attention. This is where the transformer comes in. And then again, this is how it works. You have image, you have a t, time t, you have a text prompt, you goes to noise. Noise is of the same shape of zt, the image. So stable diffusion unit. So this is essentially how the high-level picture is. We will quickly talk about the slightly the details, right? The typical unit block has several modules, right? Basically, it goes through res block, goes to self-attention, goes to cross-attention. These two are not necessarily always there. It's just for some block they have, some block they don't. And this time embedding comes here, text token comes here. So basically, this is how it works. And here you can think about it's already transformer-like, right? In the standard transformer, there's no downsampling. So the difference, there's no downsampling. And this is, if you think about this, already sufficient enough, very much like transformer. And if you look at the DIT, they actually remove this downsampling, right? This one doesn't need, they just using standard transformer. So actually, in some way, you can say, oh, UNet with this kind of transformer is more complex and diffusion transformer, because of they do use the transformer architecture, but they also use that in a more complex way. But it turns out, you could just using transformer. So interpretations, res block, local convolution, which has some prior information. Typically, this kind of CNN structure, right? So they have this kind of prior information, so that you are doing well with a bias, this kind of prior image type of geometric information. Self-attention make it a little bit more global than usually the EuroCN. EuroCN, they don't have a strong global information, but self-attention can get you there. Cross-attention is mainly for the text tokens. So basically, this is how. And this one is for some of the blocks. So time conditioning, how it's done, right? First, time you can think about very similar to position in the transformer. So this one actually treated as a position. We know there's an embedding, right? A sinusoid embedding, which is in the original transformer paper, which we talked about that. You just use that embedding, then you go through MLT, and this one gives you the embedding of time embedding. So this is actually how the timers are created. And in the res block, what you do is you project this global embedding. So this is you compute once across all the blocks. They have a block-specific projection, and then you essentially this one, and then you project that, and you add it to your latent state. So this is their implementation. There can be different implementations, as we will see in the diffusion transformer. They use a little bit different implementations for this kind of time embedding. But here is one thing which is in this particular implementation. The same time space is sent to all res blocks, but each block has its own learned embedding. So basically, roughly, this is how it works. We just quickly go through, so you just have an impression of how this implemented. That's good enough. We don't need to know too much details. But text conditioning, which is actually pretty transformer-like, right? So each one, you have a cross attention. So when you have a text clip tokens, because they generate token-wise embedding. For when you think about the clip, they can use a transformer structure, generate a token-wise embedding for all the tokens, and then you just attend to that. Basically, cross attention. You say, okay, cross attention of this guy. H is your whatever your state in your latent, and with that, and then you just similar to project to Q, project the key V, right? So for the Q, it's definitely from your UNet latent, which basically is your Q, and the key V is coming from text, right? So it's because it's cross attention, you have to compute the key and V from the text, and then you do a cross attention. So that's that's basically standard cross attention in the transformer paper. So roughly, this is how the text conditioning is coming in. And it's it generates good images. If you think about the given text prompt, it generates good images, so it's reasonably effective for this design. And they use a cross attention. You could use something else. This one also, I just quickly mentioned that the token, it's not just one single vector, right? So this is more fine-grained. Each token matters in some sense. The tokens matter because they generate this token embedding, and they actually attend for all the tokens. This is a little bit more fine-grained in terms of attention to the text prompt than if you just say a single embedding. Here is, I just want to comment on this because this is kind of useful if you are any times in the future you want to add any this kind of attention, this cross attention or whatever, right? Traditionally, if you recall, in our case, talking about the sequence to sequence, so even we recall we do autoencoder. They are thinking you are carrying out a single vector. That's typically more traditionally, right? Carry out a single vector, which will be the embedding of your whatever modality. And then you're giving that vector to whatever the downstream tasks as you are embedding. The more modern ways to do that, and including this one, including a lot of, if you think about including VLM, they are looking at multi-tokens, continuous tokens, you can think about it, continuous embeddings. And your modality, both from image or text, you generate multiple hidden tokens, continuous tokens. Then you pass these continuous tokens to the whatever downstream. In this case, continuous token is generated by clip, and they pass through this UNet. And this is more typical. And the continuous token, several tokens can represent much finer grained of your concept than you just have a one vector. So this is basically one thing. If you look at all the designs, one thing one can keep in mind. If whatever reason you want to design some kind of this kind of embedding in the future. So think about that. Based on the current, it's a sequence of a continuous token, and then you can using the transformer more effectively. Okay, so this is one thing. Now let's take a look about the scalable diffusion. This is just a quick mentioning about this UNet design, and including some modern elements of attention in there. So it's a hybrid of attention to the diffusion, to the transformer. And there are some more pure transformer structure which become more dominant nowadays, which we'll talk about. Actually, it's simpler than this UNet design in some sense. Yeah, there are no downsampling, right? So, okay, so let's look at we will talk about that next time, but let's look at this stable diffusion training versus inference. Just quickly mentioning, and this is pretty straightforward if you see the whole picture, whole pipeline, right? So image pair. So you start with that, encode the image to latent, sample T, add noise to ZT, right? So this is basically how you train the train UNet. Yeah, you're using this guy to predict noise, right? So and then optimize this on the noise prediction, right? So and then that's all. So that's you get to learn the UNet, right? Tokenize and encode the text prompt, right? Start from this is just once. You just encode that once, right? Remember, and start from a random latent noise. ZT. You repeatedly apply denoising with conditioned on the UNet. And until in the end, you can say DDIM, DDPM, right? So decode these, the last steps once with this VAE decoder. Again, the VAE encoder, VAE decoder doesn't condition on text. The only part condition on text is this UNet. So this is how the structure comes. Remarks. So the VAE is pre-trained training using encoder to predict adding noise and inference denoise repeatedly, decode once at a time. So that's basically, that's all. Yeah. So this is a pretty simple framework, but it's a practical system. Okay, so let's talk about one thing which is pretty important to increase the quality of this is widely used in practice. This is a paper by Google. So this is one trick, which is I think is one of the most important trick when people use diffusion model to generate a high quality image, so-called classifier-free guidance. There are other guidance now. Coming motivated by this paper, there are other guidances which we will not talk about, but this one is very effective. And this is one methods which you can easily use. There are also, again, other guidance schemes. So the idea, what it is, right? So basically, there's small change of training. Essentially, training, typically, we have the text conditioning, right? This one say you have a small probability, say 0.1 is a typical number. You drop this text conditioning so that you just have no conditioning. Then you use a UNet to learn. Basically, empty text, right? So you say, okay, empty text means that there's no text conditioning. And then you use that to train the UNet with a very small probability, say 0.1. So basically, the UNet can predict images both with and without conditioning. So they have an unconditioned UNet, which is an empty prompt, versus a conditioned UNet, which have a real prompt. So this is something which is needed by the training. Essentially, it has to see some unconditioned predictions. Now, how do you use that? The noise, typically, you have a conditioned noise, right? So this is what we do. But here it has a scale times unconditioned noise. Unconditioned, basically, you give that empty prompt. And the condition, you give that your whatever the prompt is, and it will times a factor. Essentially, if W is 1, it's basically the same as condition. Right. W is 0, it's basically as unconditioned. Basically, text prompt has no effect. It doesn't have anything. W is 1, which says you actually is the same as what you are training with the text prompt. The interesting thing is W larger than 1, say 2 or 3, right? So in this case, you can think about the noisy direction is more aggressively towards your conditioning. So it treats your prompt more aggressively. So it's try to do a contrast of your conditioned noise and unconditioned, and you boost that, right? Boost that by more than the factor of the prompt itself. This has a similar effect of temperature in the LLM because diffusion model, they cannot run with a temperature. So this one, the idea about this CFG is try to simulate the temperature. Temperature, usually, if you think about it in the LLM, right, sometimes you're training with temperature 1 and the generation with temperature 0.7 to be a little bit sharper so that you generate more high quality text, less diverse, but more high quality. Here is the same thing. When you make it more strong, conditioned, it tends to be less diverse, but more high quality. We will see some examples. So this is a way. So the effect of CFG is no effect when you have W equals 1 and W larger than 1 is follow prompt more strongly. So you have a C actually more strongly pattern. In the analogy of LLM, you can say that there's a less hallucination, right? When you have a training text, match the same temperature, sometimes they have a hallucination. But if you reduce the temperature, the hallucination tends to be reduced as well, and it's more high quality text. Yeah, image from but you lose diversity. So more strongly, you have more fidelity, often improves in terms of text following and image quality. Diversity can decrease because this is similar to the yeah, too large value actually can be a problem. So you have reasonable value. This depends. I mean, some 3, 5 was all reasonable. If you have a 10, 20, then it's beyond too large. So then you run into trouble. So basically, this is a case. This is actually one of the most important when you have the high quality image. The other, of course, the number of steps to generate the image, that's also important. But this one turns out to be, in addition to this number of steps, is something which you need to know. It's similar to LLMs. It's a quality diversity trade-off. Yeah. So basically, these are all I want to say about this particular CFG, and this is something constantly used both in research and in research as well as in the practice by people. So when they generate a high quality image, right? If you say I have loose diversity, you have some other ways, for example, modifying prompts and so on to change that. But the quality itself is kind of matters. So this is how this one helps. And here is an example. So 6 actually is not bad. In this is not high enough. I didn't use too high. Maybe I should give you some 10, 12, but you can try yourself. The code is there. So this one, they use the same seed. Seed actually matters, as we will see later. Basically, the prompt is, say, a watercolor painting of a snowy mountain village at sunrise, right? If you look at that, this one is just, this is the CFG1. It's basically your default stable diffusion without doing anything, basically, right? It basically says you are using this original noise network. Actually, it's I would say a little bit garbage. The image is definitely not high quality. It's messy. And this is typical. And even for this one is also not great. Visually, this one much better than this one. This one is much better than this one, right? So 3 is moderate CFG, and it definitely has a strong effect showing you have a much higher quality, both from the types of prompt following and from the point of view of visual quality, right? Both are actually better. If you look at this is Murdy. These are actually very similar, but this one generated much better. This is definitely much better. This is quality. This one starting to show off artifacts is a little bit to a kind of extreme, right? It's a cartoon-like. It's a little bit strong. Also, there's a great change. If you think about it, look at here, there are huge changes of actually. This one is more similar to this. This one is, at least for this guy, it's completely changed the picture. But nevertheless, you know, this is for 6, it's reasonable. It's not too bad. But it's, you have a stronger effect. You will see that as like a cartoon or watercolor painting like. So this stronger emphasis on that watercolor painting, right? So if you look at that, and this is at this point, I think it's not too bad, right? If you further extreme that, it will be even further. At some point, it's starting to be looking very strange, right? So basically, this is how the CFG. And clearly, if you look at that, oh, I shouldn't use CFG equals 1 in general, right? So that's by the way, in our homework, we use the CFG equals 1. It's not a CFG equals 3 because we are really just testing the things, right? So, but in general, when you really say, I want to showcase a good image generated by stable diffusion, you use a higher CFG. And this is a pretty good image, actually. Yeah, this is not, right? So yeah, so this is, okay, one thing I want to say about stable diffusion, which is relevant. We will not cover why they do this CFG, but intuitively you can see that it's stronger effects of your prompt. So that's, I think, just similar, and it works very well. So summary about spatial diffusion, then we'll move on to some experiments and fine-tuning about spatial diffusion, which is a little bit relevant to the homework. So common implementation choice in stable diffusion is work in the VAE space, right, not pixel space. And this is basically a latent diffusion. Yeah, maybe I would say it's a late UNet. And this is basically the choice, right? Cross attention for text. This is something which can be applied to many other things. Again, one thing I want to mention, which probably I will re-mention here, is instead of passing your conditioning as one vector, you're passing that as multiple tokens. And this usually is a more modern way of design choice. Classifier free guidance, you do see a better image quality and prompt alignment. So these are the things, and yeah, you can use, in our case, in both, we use a DDIM. So DDIM, because as I mentioned, when you have fewer samples, it's good not to add noise to your because DDPM, you have to have many samples because you are adding noise. Each time you're adding noise. It's actually, for many samples, it's high quality. It just, we do not have, it's very slow when you generate, because even for DDIM, you have, they say 50, 100 steps. I forgot what I used in the code. You can check, look, maybe it's 50 or 100. So it's not that a small number of steps. But then at these steps, you don't want to add noise to that. So you use DDIM, which is deterministic version of DDIM. So reduce the sampling cost. So let's take a look at this package now, right? So Hugging Face diffusers. We mentioned that is a stable diffusion. A lot of our description of this latent diffusion model is based on this particular implementation, which actually I would say the implementation is not done by Hugging Face. It's done by the people who are the original implementation was done by the researchers who did this latent diffusion paper with and then later on they evolve from there. But basically, the Hugging Face integrate that. So because Hugging Face, everybody using Hugging Face for transformers, so it's convenient to use that for diffusers as well. So you can do the stable diffusion without Hugging Face. It's just incorporate that into their library. The standard baseline is a stable diffusion 1.5. So this is one which we are doing with our basically our code. There are other checkpoints if you're interested, right? This guy typically 512 by 512. So in the homework, I think we do probably smaller, like 256, just to save the computation. Here in the notebook, we do 512 just for better illustration. So this is stable diffusion 1.5. This is typically used for research purpose. If you really want to say for the commercial purpose using, then usually you do something more. And the later versions have larger, 768, even larger, 1024, right? So this is a size which is the largest by SDXL is a very good quality with 1024. It's a little bit too much computation for us, so we are not. Also, the pipeline is slightly different than the SD 1.5, so we focus on the SD 1.5. Stable 3 is more recent, and so they have different resolutions, but typically you do this high resolution of 1024 by 1024. So this is roughly the resolutions this works with. Yeah. So this is yeah. Yeah, the first three, I will just quickly mention the first three, which is the older versions, and with a UNet. SD3, stable diffusion 3 still use latent space, but they use diffusion transformer already. And they use flow matching instead of diffusion. Flow matching, we'll talk about both diffusion transformer and flow matching, we'll talk about in the next class. But for this class, it's a stable diffusion 1.5, which using DDIM and the decoder, and the training is the same with the DDPM, DDIM, and then you have 512. So, and then you use UNet. UNet with a hybrid cross attention, a little bit of the transformer components. So this is basically how it works. And these are quick examples. Essentially, what you do, I mean, this pipeline says this is a stable diffusion 1.5, and we use half precision, right? So watercolor painting, stone mounting image, right? So this is just generating the previous example, which is in the notebook. And basically they give the prompts. This is 50 steps, I think. And guidance is 3 or something like that. Tokenize the text, sample latent noise, run the scheduler loop, right? And then basically, it's just do everything for you. So you essentially you can use this pipeline, and they aggregate all these components, components related to this model. The components including this tokenization, including this VAE, including this loop, including, and then you also have including this glide balance. So once you have these guys, and then you are done. So basically, this is just an illustration of how easy it is to use this code. You could use, for example, you can use stable diffusion 3 if you want, right? So then they will generate a better quality images with a higher resolution. Yeah, so basically that's about this. We will talk a little bit about the fine tuning. The reason we talk about fine tuning is one is related to homework. The other one is it's practical, and also it's not described in in other lectures. We have since we don't have a lot of time, we just briefly mention the high-level ideas of that. So Hugging Face diffusers exposes several common small data fine-tuning methods. And then they essentially have a few things which is relevant. One is text inversion, which is in the notebook. The homework doesn't allow ask for that. Homework is for the UNet, just the direct fine-tuning. Text inversion says the following. So you basically insert a new token. New token, for example, we will see the examples. Basically, new token says whatever token you give. It's a token says you can give anything which is not appear in the original token dictionary. Then you keep the model fixed. Use for concept or style from a few images, basically. Basically, okay, this one says what you are actually learning is just the token embedding. You are not learning the UNet model. Where the token embedding is. Token embedding, if you think about that, the clip output, right? So then you have this token embedding, so that they will be used for the transformer, right? For the cross attention. So you're modifying part. You are learning that. Yeah, you for the new token. Yeah. So basically, this is something. Dream Boost rare token. Again it's a similar. You also add a token. Essentially, usually what it is used for is to a subject. For example, if you want to say I want to generate a particular cartoon figure, right? The cartoon figure probably the stable diffusion either never seen that or it's not been strong enough in your training data. So if you just say, oh, this cartoon over give that the name of that cartoon, or I mean just person, they probably cannot generate well. So then what happens is you give them a few images like that, then you try to learn associated with this cartoon or whatever the figure subject with your with your new token. Then once you use the new token, they will start to generate that. So essentially, this is how it actually works. It's more like a personalization. Use a rare identifier token and fine-tuning model weights for one particular subject. It also has something adding price preservation. What it does is means that it's try to say, without this, it try to prevent overfitting. For example, you say a specific dog, right? It's a maybe black dog, but of a specific. It's your dog, for example. That's different from other black dogs, right? Then you say, okay, I want to generate this token. Say you just say that is call it A token A, whatever. And then you say, oh, generate this, and then they should generate this. But if you say black dog, they should still generate a generic black dog or something like that. So this prior preservation is trying to add some regularization using the image generated by the original model on fine-tuned model as a regularizer, so that for the prompt of generic prompt like black dog without this special token, right? And then you want to say, okay, without special token, you should behave similar to the unfine-tuned model. And with this special token, you should be doing something associated with a particular fine-tuned image you have. Yeah. So this is what it does. So essentially, it's more isolated. It's a better isolation than say text inversion. If you think about that, because of this prior preservation. You can say, okay, I have a specific person if I want, or whatever, just a few images. I can use that to identify this special token with that specific subject. And then, but without hurting other subjects. So if with this token, you show this subject. Without this token, you are showing normal diffusion. Right, so this is how it works. So this is a little bit more heavy than this guy, right? LoRa, of course, we know a lot of LoRa in the LLM. It works very well, actually, for stable diffusion. So you can use a LoRa to train adapter and so on. I think in our case, we make it simple. We are not training LoRa. We just train the whole new UNet in our for our homework, right? So, but basically, this is some of the common fine-tuning methods. So we use a little bit simpler, just training the whole unit. Actually, in the notebook also we have two versions. One is something mimicking the text inversion. The other one is just the unit, right? And we are not doing this thing. Yeah. So that's about what it is for the some of the fine-tuning methods. Particularly this one, if you think about this one, it's pretty reasonable, right? So it just says identify special token with a subject, fine-tuning while preserving the ones without this special token. Now you can generate pretty reasonable images targeted for this special token. Yeah, textual inversion is the lightest effective because subject LoRa is pretty generic. LoRa, of course, we do that for LLMs, we do that for stable diffusion. So this is a pretty popular method. So here is one example. It's just one photo of this particular cat. So we want to say generating fine-tuning so that we generate the image when we say something cat will be similar to this. So there's a photo of a small cat toy, and we use that to fine-tune stable diffusion. Basically, we have two UNet fine-tuning, the whole UNet. This is similar to the homework. On the image passion pair. So we just have one image, and then we just randomly generate many times, text inversion. this is a simulation of text inversion, right? So keep the model fixed, just learn one new token embedding. In both cases, we compare before after generations, right, with the same seed. The same seed is important. Once you change the seed, you modify, right? Same guidance, because we know looking at our earlier CFG result, 3 is pretty reasonable. It's not too much artifacts, but it's somehow it's a higher quality, right? So we don't want to use CFG equals 1 because quality may be not there. Based on our early example, right? If you see the quality is 1, it's kind of, it's not garbage, but it's not that great. The training prompt and 1 out of training prompt, okay? Basically, training prompt is this guy, right? This is only training prompt. So this is a training image with one training prompt, a photo of a small toy cat is your training prompt. And there will be also modify this training prompt to say 1 out of a training prompt, another prompt, related prompt, and then we will do that. Okay, so this is the experiments we try to do. And basically, yeah, I think UNet change the denoiser itself, and it will be generating images. So you'll see more like this. So it's kind of text inversion generate a special token, right? So I think quickly fine-tuning, train the West derived on image pair, I just quickly mentioned, right? So in the notebook, they add them with this guy. I think later, yeah, so something like that. And this one is 400 steps and so on. So this one because you are training whole networks, so you need a smaller learning rate. Otherwise, aggressive update, too aggressive. This one you can have a higher network because you are training a very small number of little bit network. Yeah. So you are not doing that. Here the example. Fine-tuning results, right? So basically, this is top is before the fine-tuning, generated a photo of a small toy cat, right? It doesn't look like a toy cat. It really look like a real cat. So it's not exactly prompt following well. And after fine-tuning, using that particular image, if you look at this, the color, this seems to be a little bit similar. Color, this guy a little bit similar. Color, I mean, seems they're pretty similar color. But this one is more like the one we showed the image, particularly this one, right? If you look at this one, this image, it's actually, they're using the same seed. Yeah, same seed actually means the same original Gaussian noise, the same ZT, big T, right? So that is the same. But then, this one also looks like that one, I would say, right? This is slightly strange. So sometimes because you have one image generate, one image fine tuning and so on. This one is not. So this one is basically you're fine tuning the whole neural net, and this is how the results like. This is a training prompt, a photo of a small toy cat, right? So basically, and you see that it's effective, the fine tuning. It does generate something similar. This outer training prompt is a cartoon toy cat, right? They're the same as before. The toy cat is there, right? So playing with a girl. So basically, there's a little bit of, I mean, I don't know. So I think because of fine tuning a little bit, you are seeing somehow the girl is a little, I mean, it's there, but a little bit strange because there's a lag here, doesn't seem to be entirely connected. But you do see a toy cat here, which are very similar to the one we show. So it does try to tend to there. And here, I don't see a girl here. So this one has a better prompts. But this one is again somewhat similar to this you are showing, and but the girl is a little bit strange. This one is also a bit, I don't know. So, but overall, this one you can see from this cat to this cat. So it does generalize. All I say is generalize to other prompts, right? So not only on the training prompts, and this guy is again. I would say this feel a little bit more cartoon. I don't know. Maybe it's not. Maybe it's something. But the cartoon doesn't seem to be showing too much. A cartoon toy cat. But maybe maybe this prompt is a little bit ambiguous. Maybe I should change to a different prompt, because cartoon, it doesn't say what it means. Maybe it's a cartoon toy cat and a toy cat. Maybe they feel they are not too much difference. But anyhow, so this is something you see. And again, because they are same seed, right? So they tend to be similar, these images. You can see the seed matters, and they tend to be similar, but you modified it. This is a UNet fine-tuning. This is a text inversion fine-tuning, right? So again, the same image, because same seed, the same original image before fine-tuning. This is after fine-tuning, right? So if you look at the text inversion, I put this token, so basically of this guy, before the text inversion, after text inversion, and so on, right? So this one is, yeah, this one, I mean, this one looks kind of, to me, it's a little bit interesting in the sense of, this one clearly not like the original toy cat I showed, right? If you look at the original toy cat, it looks like, maybe let me see what it looks like. It's like this, right? So it's original toy cat. It doesn't, but it has this flavor. You can tell the features from that. So, actually, it's interesting to see that this one is more like that. But this, but it's more. That definitely has the features. So it definitely has certain features of that. It's a color rainbow or whatever, and this tail or whatever. Some you can recognize certain features, but it's not quite. And yeah, this one has changed the color, but this one has a somewhat color influenced by this one. I would say this one has a color influenced by this. So you can see these different things has something preserved. Again, this one is the other prompt, is outer sample prompt. So yeah, basically cartoon toy cat. I think when we have this, we should photo of this guy. Toy cat replaced by this. This is the same thing. When you have the text inversion, you replace this toy cat by that special token. And then, yeah, this is the same before this. Again, this one you can tell. But essentially, what I can say is the following, right? So it does try to push your generating this special token to something mimicking the fine-tuning image I showed, that particular toy cat. But this one modified quite a bit. You do recognize some features. You do recognize some features here. Yeah. So, but you are not quite the same. Anyway, so this just give you some information about it actually can be done. People can play with that, and in particular, people use LoRa quite a bit. Just play around with this kind of fine tuning so that you can target to whatever you want to generate. Now with the stable diffusion. Yeah. In summary, so UNet is a good backbone for denoising, right? Its a variance for diffusion can be at conditioning and attention, right? Latent diffusion makes a high resolution generation practical in latent space. So this is something which people use. You are reducing 256 image size to 32 image size, which much more efficient than peak space diffusion. So this is used in practice. Stable diffusions, right? There are a few things which we mentioned: the VAE for compression to latents, text encoder for conditioning, and the conditioned UNet for denoising. We talk a little bit about how this condition is implemented for this particular UNet design, and a sampler for generation. So what's next? Next will be next class, which will be the last class before our final exams, right? So there will be the third exam, which for the part 3. But what's next will be first, can DDIM be improved? The answer of this, of course, is a flow matching. So we will talk about that. And this one is more widely used than nowadays. People try to, I will tell why. I mean, I will mention why in the next lecture. This, I want to say it's improved in some sense. It's actually, from practical purpose, it's kind of more convenient, definitely more convenient flow matching than the DDIM. Both are deterministic. Can UNet be, of course, this one is DIT. So these both are the topic of the last lecture. Then we are pretty much done with all the class. And this is a kind of a references and including these fine-tuning methods. You can look at the descriptions and so on. Okay, thank you. Okay, we are done for today.